Hi, everybody. My name is Connor Bush, and this is my submission for homework 4, part C. So the biggest part of this homework portion is going to be extending our analysis from all of the feedback control and transfer functions that we had from part B, and then we're going to do some um, sort of frequency analysis with that, looking specifically at this Bode diagram. So we're going to first plot the Bode diagram for the open loop response of the system in part B2. So that is where we received our forward transfer function. So what that kind of looks like here, we're going to be using scipy.signal. We have this library implemented, so we can just do sig dot and then the Bode. If you look here, our inputs, we just need some sort of system. So we're going to input our transfer function from part B, and then it returns 3 different arrays: the frequency array, the magnitude array, the amplitude in decibels, and then our phase array or the phase lag in degrees. So if we input our transfer function from part B, that was our forward transfer function, since we're just considering an open loop system. And then we need to give 3 variables here because we have the 3 arrays that we're outputting. So W for omega for the frequency, dB for the amplitude in decibels, and then phase for the phase lag in degrees. So in order to get the Bode diagram, we need to plot these like decibels versus frequency, and then the phase versus frequency. So I'm going to copy this for the subplots just for the sake of time, and then update accordingly. We have now 2 different plots, and we want to keep that all together. So we have that in a 2-row, 1-column situation. Our x-axis will be our frequencies, omega or W, and then our y will be decibels. This will be, I'll just name it decibels. Similarly, our x-axis for the second plot will be our frequency versus our phase lag, just phase. I'll name that phase lag, and then that is in units of degrees. We need to specify what row and column each of these plots are in. And then just update this really quick. So as you can see, this top plot is our frequency versus our decibel plot, and then this is our frequency versus our phase plot. I'll kind of go into further explanation as to what both of these mean and how we can determine the stability of our control system by looking at these diagrams. So that kind of is what we are looking for part C1A. This part B, we want to determine the amplitude ratio from a given frequency of 1 radian per second. And then we're going to compare from our graph above from part B. So to kind of go back to this here, as you can see, we can input a frequency here. So we want to say that our frequency is 1. And then if we look at what is being calculated for the decibels, this LF is what we're measuring from this function here, the Bode function. So if we rearrange, because it's a logarithmic scale, if we do 10 to our decibels divided by 20, we can get the amplitude ratio that we are looking for. So if we do that like this, and then ask for the amplitude ratio, we see that the amplitude ratio is less than 1, so it's 0.64. So if we look at our input versus output, our input amplitude is about 1, and then our output amplitude is about 0.64, so it's very close. So if you divide, you get the 0.64 roughly. So that is kind of how you can calculate the amplitude ratio instead of just looking graphically. So now we want to explain what crossover frequency and phase margin is and how this relates to the system stability under feedback control. So crossover frequency, we need to reference this graph down here. I'm going to update the x-axis for both into a logarithmic scale so we can get a better idea. I'm going to get rid of this, revert back to what we had prior. So the crossover frequency is if our system crosses this negative 180 degree like mark, that's when our system is reaching instability. So at that point, it's around 1.15. So if we go up, or let me take a step back for a minute, our crossover frequency is that point where it hits that negative 180 mark. So our crossover frequency in this case is about 1.15 radians per second. And then if we go up here, and if we look and see that our decibel range is less than 0, then that means our system is stable. And that kind of relates back to here. If we look at this amplitude ratio, if this comes out as 1, then the log of 1 is just 0. So if we hit, this kind of goes into, I guess I can explain that now. If we are, like, let's say our crossover frequency is above that 0 mark, that means our system is unstable. If it's below 0, that means our system is stable. What was the other part? Phase margin. So phase margin is when we look at where we are at 0 here in this decibel or frequency versus decibel chart. We go down and then we look at what degree that is at. So that's at 173. So our phase margin is the difference between what we are here and that negative 180. So roughly around 10 degrees is our phase margin. And that's just the distance from where we are at that 0 mark in our decibel chart from instability at negative 180. So that kind of explains crossover frequency and phase margin. And then obviously because, okay, so we look here at our crossover frequency, our decibel reading is negative. So that means our system is stable. If we look up here, again, our input amplitude is greater than the output amplitude. That's another symbol of stability in our system. And then if we look here, these oscillations are decreasing, meaning our system is stable. So if we want to take a look in this part D and E at what an unstable system looks like, we can increase our proportional controller gain from 1 that it is now to 3. So if we go up here and change this to 3 and take that all the way down. So we want to look at the Bode diagram for this one. So obviously, so we hit 180 around here. This is our crossover frequency. And then if we go up, we see that our decibel reading is greater than 0. It's positive, meaning our system is unstable. We can look here, we see that our output amplitude is greater than our input amplitude, meaning that the oscillations are increasing. And then that is, you can obviously see that here as the oscillations are infinitely increasing. So that kind of is everything to do with the amplitude analysis. And frequency analysis for part C, we explored what a Bode diagram is and how we can determine the stability of our feedback control system. So yeah, let's dig into part D. Thank you.